Hi, this video is about projectiles that are launched at angles once again, but one additional twist. In this case, they're landing at a level, at a vertical position that's different from their starting position. So previously we've done projectiles launched horizontally and then projectiles launched at an angle, but they started and ended at the same height, at the same vertical position. And now we're doing it launched at an angle, but landing at a different vertical position. So this is a bit more advanced, but the process is the same. So let's imagine that we have a projectile that's launched from the edge of a cliff. Cliffs play prominent roles in physics. And let's say that that cliff is 27 meters high, and the projectile is launched at 20 meters per second, about 40 miles an hour, at an angle of 40 degrees with the horizontal. Where does that projectile land? How far away from the bottom of the cliff does that projectile land? So just like we always do, we'll sketch the trajectory and we'll start labeling things that are important to us on the trajectory, specifically distances, original speeds, final speeds, and the velocity components. That's what we do with the things launched at angles. So I've redrawn the cliff and the trajectory here of the projectile, and I have the initial conditions here in one color, 20 meters per second and 40 degrees. And then I went ahead and separated that into its components. So the vertical component would be 20 times the sine of 40, and the horizontal is 20 times the cosine of 40, and I drew those arrows there to represent those components. At the very top of its path, it has no vertical velocity, but it still has a horizontal velocity. That never changes. So 20 cosine 40 for the horizontal velocity. Now when it comes back down to the same vertical position where it started, see I drew a kind of a dash line there from the edge of the cliff out, we know something about the speeds at that position, or the velocities at that position. We know the horizontal is still the same, 20 cosine 40. And we know the vertical is just opposite what it was to start with, because whatever gravity takes away on the way up, it gives back on the way down. And so instead of 20 sine 40, I wrote negative 20 sine 40. Way over here at the end, we know the horizontal speed is still the same, 20 cosine 40, but we don't know what that vertical velocity is there. That's something that we could calculate, I suppose, but we don't know it offhand because it's going to speed up from this value as it continues to fall down towards the ground there. The other thing that you'll notice is that I marked this vertical position here as negative. So remember, our convention is to use positive for right and up and negative for left and down. And so I wrote this as negative 27 meters because it ends 27 meters below where it started. And so those are my initial conditions and my labelings on my sketch. We'll convert that into data, our givens and unknowns, on our x and y columns. In the x, we're looking for that horizontal displacement. We know the average speed horizontally is 20 cosine 40. It doesn't change. The acceleration is 0 in the horizontal, and we don't know the time. In the vertical, we know the delta y is negative 27. We know the initial vertical at the very beginning is 20 sine 40. The final vertical we don't know. It's bigger than 20 sine 40 and negative. Acceleration is negative. That is, it's down, 9.8 meters per second squared. And the time is unknown. So it would be pretty easy to find this horizontal distance if we knew the time. And so like so many other cases that we've done, we're going to find the time in the vertical and then use it in the horizontal. Those are my notes down here. The trick in this case is that in the vertical information, we can use this equation, which remember is a second order polynomial. It's a quadratic equation. And so I wrote that down. That's your equation on your toolbox, on your card. And I plugged in the numbers, my equation, and then my substitutions. And that's a quadratic equation. So what I did was I put that in what's called standard form so that the powers are decreasing to the right. So t squared, t, no t equals 0. And then I kind of simplified things. So the coefficient on the t squared is negative 4.9. The coefficient on the t term is 20 sine 40. And the constant there is positive 27. It's positive 27 when I move it back over to the other side. And that equals 0. At this point, I have three options. I can either use my calculator program to solve for t, a quadratic equation solver in your calculator. You can graph the function, graph the equation, and see where it crosses the x-axis. Or you can use the quadratic formula. If you forget how to do those things, go check the other video on the quadratic formula that I made to remind yourself how to do that. Once you solve it, I use my calculator, a little program on the calculator to do it. I got two answers for time. I got time is either negative 1.377 seconds or time is positive 4.001 seconds. It's the positive time that I want. What does negative time mean? We'll come back to that. It's the positive time I want. It takes that projectile 4 seconds to go up and come back down. And so I plug that over here in my X column data, and I'm going to use this equation. I made my substitution, and I solve it. So it turns out it's about 61.3 meters away in this case. So the tricky bit, I guess, the new part, is that you have to really pay attention to those signs. If it's ending lower, then the displacement vertically is negative. If it's ending higher, the displacement vertically is positive. Maybe it lands on the side of a hill or something like that, which is kind of interesting. The other bit I want to say is that sometimes in math class, we just kind of throw away the other answer, or we have to write both of them. But in this case, this time, this negative 1.377 seconds, is the time for something to happen. And I would challenge you to figure out what that is. What's 1.377 seconds the time for? Something to do with that problem involves that time. See if you can't figure that out. And let me know if you have a good idea.